Okay, so now I want to take a bit of a detour, and I want to talk a bit more about image representations. So just to get an idea, and maybe just to make you move a bit, who here is comfortable with dealing with images in programming? Who has already done some image processing before? Okay, so we have about a quarter of the crowd. So this is good, because if you've never dealt with images before, you might not even know, how do we even represent an image to a computer? So this is what this section is going to cover. How do we represent an image to a computer? And then you'll kind of hopefully understand where that fits in the context of convolutional neural networks. So let's start with an image representation. So typically we speak of an array, we say an image is an array of pixels. So to the computer, when we take an image and we upload it to the computer, we really represent this as a matrix of numbers. And these matrix of numbers can be represented in different ways, but typically if we have, say for example, a grayscale image, what we do, so a grayscale image means a black and white image. What we do is we vary the intensity of how black or how white a pixel is. And you can really think of this as a light bulb. The pixels in your screen are a light bulb, and you decide how much you turn it on or off. So if it's at 0, it's completely off, which represents black. And if it's at 255, it's completely on, which represents white. And everywhere in between, you can get these different shades of gray. And by varying this amount of gray, you can then get a grayscale image or a black and white image. And usually when we have one grid of pixels or one matrix, we refer this to as a channel. So again, a grayscale image has a single channel. And here we have an example. So we have a digit here, the digit 8, which is represented by a 28 by 28 grid. So we have 28 by 28 pixels for a total of 784 pixels. And you can see from this image that this is how we represent our image. So mostly black everywhere, so zeros mostly everywhere. And in the center, where we have some brighter points, we'll have some values between, usually closer to the 200 range. So you can see here we have some values at 221, 249. And again, this is taken care of by the computer. When you click on the image, this is what's being shown. It's the computer telling the pixels how to light up. But this is what we're giving to convolutional neural networks in the context of images. This is how it interprets these images. It can then do all these mathematical operations based on these values. So if we do a 2D convolution on a grayscale image, this is essentially what we're doing, right? We have our kernel, and we slide it over the entire image. And then based on the features that it's learned, that the kernel has learned, it can then decide, well, what did I detect, and what can I say about what I've detected? So in this case, as it passes over, say, the bright edges of the 8, it might fire up in some specific way. And when we combine many, many of these kernels in many different layers, then we can get a good confidence that we've detected an 8 in this image. So now let's go on to color images. So to display colors, we have 3 of these channels. So in the grayscale image, we only had from black to white. Now we have this RGB representation. So we have 3 channels, one representing red, one representing green, and one representing blue. And when we have an image, we decide how much red, how much green, and how much blue do we want for each pixel. And again, it's really just light bulbs underneath the hood that are going to turn on and off based on a certain intensity. So here we have the first ever image created by an RGB, the first ever color photo created. And this was actually created chemically. So they had different plates that would react to red, different plates that would react to green and blue, and they would superimpose them to get this final rich image. Now to give you an idea of what I mean, oh, I don't have access to this video. Hopefully this works. This is a really cool yes, okay. So this is a really cool demonstration of RGB. So let's look at this experiment. So we have, is it playing? Yes. So we have a laptop. And the person has taken an image, an RGB image, and split it up into its R, G, and B components. So we have the R component of the flower, the green component of the flower, and the blue component of the flower. And in a very clever setup, he took these CD cases and is going to now reflect the red, the green, and the blue on the CD cases. And what's going to happen is that as he turns the computer, right, these are going to add together. And you're going to see what happens. So the red, green, and blue add together. And now we have this reconstruction of our full image. So this is really just a really neat demonstration as to how the red, the green, and the blue channels can add together to give you a full image. Okay, so now that we've seen some image representations, let's look at how to do our 2D convolution on an RGB image. Because up until now, the convolution examples that we've seen was for a single channel or a depth of 1. So now what if we have multiple channels? So, and again, typically in general, when we do a 2D convolution, we usually deal with a volume as an input. So what this means is that each kernel will also be a volume. So here we have our input image. So say we have some pixels, weight and height in pixels, and a certain number of channels, or depth, which here is 3, so our RGB. Then our kernel will have a volume of f by f, which is the spatial extent of our kernel, so in this case 3 by 3, and will also have a depth of 3. And the resulting output, feature map, will have a volume of W out by H out, which we can compute using our arithmetic. But what's really interesting is that it'll only have a depth of 1. So we're actually going to sum up all of the outputs together to produce one single feature map. So let's break this down into details. The first thing that we want to do is we want to separate the inputs and our kernels by channel. So we have our RGB image, and we separate the 3 of them. We do the same thing with our kernel. So we declare our kernel, and then we separate them by R, G, and B. So we have a kernel associated to the R channel, a kernel associated to the green channel, and a kernel associated to the blue channel. We then perform our 2D convolution on each channel. So these are the convolutions that we've seen up until now, and this is the same examples that we saw before. And we have 3 feature maps that are created. Then we sum the results to get our W out by H out by 1 feature map. So let's look at an animation that shows the entire procedure. So we have our RGB channels, we split them up. Now we perform our convolution. So again, this convolution is done for each feature map. So in a sense, the network has to learn for each feature map what to focus on. And then we sum them together. So to create depth, we simply use multiple kernels. So here we have our RGB channel, and now we can declare multiple sets of kernels. In this specific example, we use 4 sets of kernels. So by using 4 sets of kernels, we'll now have a depth of 4. And this is a really important concept. This is how you go from volume to volume in convolutional neural networks. So again, the general case for a convolutional neural network is you have an input as a volume, and your output is a volume. And now if we continue, we had a depth of 4. Well, now we can use, say, for example, 8 kernels and have a depth of 8 on our output. And you can imagine how you can get this very rich set of representations. And it can become very difficult to interpret these as you go deeper and deeper into your network. And again, the idea is that you want your neural network to figure out the optimal parameters for these sets of kernels. Now let's look at another kind of operation, which is the one-by-one convolution. So one-by-one convolution is very useful in the context of channel reduction. So what that means is you can often get to the point where your volumes get really, really large. So you have multiple channels, and you want to reduce them to reduce the complexity of your network. So typically, the one-by-one convolution is used. And of course, if you use a one-by-one convolution on a depth of 1, that doesn't really make it's not necessarily a useful operation, but it's very, very useful when you have multiple channels. So here, the network can learn how to, in a sense, average these channels together to reduce our feature map size. And what's really interesting is that because we're defining this as a one-by-one convolution, we can then add some nonlinear activations. So when we're using the one-by-one convolutions, we can then add a ReLU or a tanh after this, and this gives us this gives our network the ability to have some representations that are a lot more complicated than, say, just an average.